Ah, great. Okay. Oh, that's a nice 3D printed battery holder. Okay. I hope the microphone's okay. Yeah. So last time we finished with basically the definition of prismatic cohomology, and now we want to see a little bit about how to compute this. And so today we will hopefully talk about prismatic envelopes. So first of all, so the one example we saw yesterday of prismatic cohomology was this example where my A mod I algebra was just A mod I itself, and then we just get our prism back. So that was not very interesting. Generally, this prismatic cohomology of some A mod I algebra R, and also this reduced version. Remember, that was the global sections of the sheaf coming from, like, that assigned the value B mod J to every object in the prismatic site. These can have a negative homotopy. Right? They're derived limits, so they can have some derived stuff. I'm always in homological grading conventions, so cohomology for me lives in negative degrees, so don't be confused by this. So this can have negative homotopy. And in order to kind of understand that, we have to somehow try and give names to elements, right? That's always what you have to do. And so observe that on the prismatic site, we had this ideal J, and so we can take powers of that. So this powers of this gives a filtration on this sheaf, this structure sheaf on the prismatic site, right? This to every B comma J assigned just B, and this assigns like the ith power of the invertible ideal that I have on B. So this gives a filtration with associated graded given by the sheaves J to the I mod J to the I plus 1. And now it turns out on global sections, we get a filtration of prismatic cohomology. And it turns out that filtration, so a priori global sections of some invertible sheaf are of course not necessarily an invertible module, but in this case, it turns out all these J are actually base changed from the ideal that I have on A. So this is a little lemma that we'll see later in some different role. So let me not prove this here, but it turns out that if you have a map of prisms taking the ideal into the ideal, then you can actually check that the ideal on B already has to be the tensor product, has to be base changed from the ideal on A. So this is a little lemma about delta rings. This is also the main reason why these ideals were defined in the way they were, where we require that they're locally generated by some element D whose delta is a unit. We'll see that in action later, but here the consequence is that this gives a filtration on prismatic cohomology whose terms can just be identified with twists of prismatic cohomology by this ideal, right? We're tensoring with an invertible ideal, so that commutes with limits. And so this has associated graded terms. And no, I shouldn't forget. This is the wrong one. This has associated graded terms, well, given by this, which we can also write as prism bar, which is the mod I reduction of this, base changed along A mod I to I mod I plus 1. So in some sense, this is a twisted version of this prism bar guy. So this has a name. It's called prism bar, and then there's this twist I. So let's take that as a definition here. So we have a filtration on this mysterious complex prismatic cohomology, and it's essentially by copies of the same thing, right? Just maybe twisted. So what do we get if we have a filtration and we somewhat understand maybe or pretend to understand the associated graded terms? We get differentials between them, right? We get some connecting homomorphisms. So we get a connecting homomorphism in this case, or think of this as some kind of Bockstein, right? I mean, if you do this for the p-adic filtration on something, like on, say, singular homology, you really get like a Bockstein homomorphism. Yeah? Yes, I mean, this guy here, since I was a line bundle over A, this guy is a line bundle over A mod I, and so you can also think of these as like invertible prism bar R mod A modules. Yes. And now we get a connecting homomorphism, which goes from the ith guy in your filtration to the next guy, and it's homologically of degree -1. It goes into the suspension, right? Cohomologically, this has degree +1, right? So we get these. Sorry, there's an I plus 1 here, right? We go into the next layer of the filtration, and let's maybe just call this D. And well, one also has a map from R to prism bar R mod A, right? Since this was the limit over the prismatic site, op maybe. I was told I messed up some of the ops yesterday. Limit over the prismatic site with pointwise value given by B mod J. And remember how the prismatic site was set up. Each of these B mod J came with a map from R. So we have a map from R into this limit. And now what we see here is that somehow this prism bar thing is an algebra over R. And it comes with these kind of differentials. At least there's this twist. So this together makes the following direct sum into a CDGA. I guess I haven't said why this is like a derivation, but that's something you can work out. Right, so you have these connecting homomorphisms here that have homological degree -1 and increase the twist. You have an action of R on the 0th term, so this makes this into a CDGA over R. And you see kind of a similar story as we saw yesterday in Ben's talk, where somehow you stare at Hochschild homology, you produce a map from R into HH0, and you figure out some differential on there, and suddenly it has something to do with de Rham forms. And the same thing happens here. So you have to prove a little bit more. You have to show something that like elements of the form dx squared to 0. Let's believe that, and then we get a map from some de Rham complex into here, and here's what you can say about this. So this is called Hodge-Tate comparison. So, yeah. I think so, yeah. Yeah, this should be in this Bailenson filtration that Ben described yesterday. Take this filtration that we have there, this is called the Hodge-Tate filtration. That's why this will be called Hodge-Tate comparison. And then this is just pi 0 in this Bailenson T structure. This gives you this chain complex. You can also think of this as like in the associated spectral sequence, some kind of diagonal that goes through 0 and is parallel to whatever direction your differentials go in. So yes, this chain complex, that is identified by this Hodge-Tate comparison theorem. This is, if you want to look at it more closely, let me give a reference here. This is theorem 4.11 in Bad Scholze. This is saying that if R is smooth over A mod I, the canonical map from the de Rham forms, or the de Rham complex of R relative A mod I to the direct sum as here. Let me maybe write this as pi minus star prism bar R mod A star is an isomorphism. Of CDGAs, yes. And in particular, right now we have these annoying twists. This may be not what we actually wanted to understand. We wanted to understand the untwisted thing, but in particular, this tells you, I mean, you can twist back, right? As Lars asked about earlier, this is like a line bundle. So we can twist back, and in particular, we get that pi minus I of this prism bar guy. I think people now call this Hodge-Tate cohomology. Can be obtained by taking this de Rham complex and twisting it back like this. I mean, I could write this like this, or I could put like A mod I and I mod I squared to the minus I here. Yes. Right, so essentially, this means that essentially this prism bar guy is something we already know. It's de Rham forms. So one way to think about prismatic cohomology is that it somehow glues these together in a very interesting way, right? And this is somewhat related to this thing that we saw in the first lecture, that maybe THH of some FP algebra is, well, some FP algebra, but then TP somehow glues these things together in an interesting and very non-trivial way. So this is one way to think about what prismatic cohomology does. And this is kind of your main doorway into controlling this thing, because, yeah. No, term-wise, right? This is okay. So the question was, do I mean this term-wise, or do I mean this is like a quasi-isomorphism or complexes or so? No, this is really a statement about CDGAs, right? This really means this, right? It really means that the minus I homotopy group has an interpretation in terms of omega I, of the abelian group or the module omega I. Right. And so for this is kind of your main way of controlling prismatic cohomology. For example, we directly see that if R is smooth of dimension n over A mod I, then prism bar and all its twist, and hence also prismatic cohomology itself, is concentrated in degrees between minus n and 0, right? Because if you're smooth of dimension n, then your de Rham forms are only going to go up until omega n, and then you get the same statement about prism bar, and then because this guy is filtered by twisted copies of this, you get the same thing for the whole thing, right? So we don't yet know how to compute this, but we already know something about in which degrees we should expect it. The question was whether there could be a lim 1 in principle. So prismatic cohomology, this is a complete filtration, which I think means there's no lim 1. Okay, maybe there could be one in principle. I mean, yeah, I guess, right. So maybe in principle there could be, in this case, since this filtration, at least locally, it's really like an adic filtration by powers of some element, right? This ideal is locally principal. Everything should be fine, right? But you need that this is complete with respect to that filtration, otherwise you could have problems. Okay. That's what we just discussed, that somehow so the question was why do we get that also unreduced, like just prismatic cohomology is concentrated in those degrees, and that's because we have this filtration on prism R relative A whose associated graded terms are all just twists of prism bar. And if you have a complete filtration and modulo this discussion about potentially lim 1 terms, this gives you a spectral sequence to compute the homotopy groups of prism from the ones of prism bar by and it's just concentrated in some strip. So yeah. Now similar to what Ben did with the HKR filtration yesterday, with the HKR theorem, you could now also try to take this statement about homotopy groups and extend it from the smooth case to any case by doing some kind of colimit extending in the argument R along sifted colimits, right? You can write every ring as like a sifted colimit of smooth ones by doing a simplicial resolution, and then you could try to formally extend both sides and see what you get. And in general, so prismatic cohomology, as we defined it, does not commute with sifted colimits in R. And here maybe, let me really write like R gamma of this O prism R relative A. Because somehow sifted colimits can also produce stuff in positive degrees, and this thing was obtained as a limit of discrete things. It only lives in negative degrees. But for R quasi-symptomic over A mod I, so there's a condition on in which degrees the cotangent complex lives. This problem does not occur, and in general, one wants to replace R, this guy, by the left Kahn extension from quasi-symptomic R. So this is like a minor technical point. I'm just saying in general, like if you want this to behave well in full generality, you need to kind of derive prismatic cohomology as we've defined it so far. That breaks some things, namely it breaks some versions of descent that you in principle had before, but somehow it doesn't break whenever things are quasi-symptomic, everything agrees and everything works. So I don't want to go into detail about this technical point. I just didn't want to say anything wrong. Wants to replace by the left Kahn extension from quasi-symptomic R. But for R quasi-symptomic over A mod I, this agrees with the derived version, the one where I restrict to smooth guys and left Kahn extend from there. So yes, so I guess in yes, I could say or smooth. Because yeah, or polynomial, yeah. Right. This is supposed to be like a minor technical caveat. In all the cases we will be looking at, we will be in this quasi-symptomic situation, and this derived thing agrees with this. And that also happens in the Bad-Scholze paper. At some point they point out that in full generality one wants to take this, but they don't introduce like a separate symbol for that. Yeah. So what do we get if we take that statement over here and we somehow want to derive it in R? Well, the sort of functorial way of thinking about homotopy groups is that they're the associated gradient of the Postnikov filtration. So if you take that filtration whenever R is quasi-symptomic, or whenever R is smooth, sorry. So if you take that filtration whenever R is smooth, you know its associated gradient agrees with that. So if you derive from the smooth case, if you left Kahn extend from the smooth case, you won't get necessarily something that still agrees with the Postnikov filtration everywhere, but you get some filtration whose associated graded is the derived functors of this. So let me call this derived Hodge-Tate comparison. For R quasi-symptomic over A mod I, there is an ascending filtration called the conjugate filtration on this prism bar guy. It's ascending rather than descending because like this f smaller equal I corresponds to tau bigger equal minus I. This is somehow flipping the indexing around. And this filtration has associated graded given by these derived de Rham forms of R relative A mod I. And then pi minus I lives in degree -1, so here I should put like the shift to degree -1. And also this whole thing has this twist along like A mod I with like I mod I squared to the minus I, right? So we get some, like we're now 2 filtrations deep, right? This guy itself was somehow one part of a filtration on prismatic cohomology, and now there's another filtration on that that cuts this apart really into copies of de Rham forms, derived de Rham forms. So what does this get us, right? I mean, in the smooth case, somehow this is as good as talking about the homotopy groups, but there's one other case where this can be described rather explicitly, which is the following. So, yeah. You mean whether the inverse limit is 0. This is like only non-trivial for non-negative I. Right, this is an ascending filtration. The inverse limit is just 0. You could ask whether it's exhaustive, and I think it is. The co-limit should always be everything. Right. So let's look at the following case. So if your ring R is the quotient of A mod I by a regular sequence, what do we know about the cotangent complex, like L omega 1? In that case, if you quotient a ring by a regular sequence, the cotangent complex will be concentrated in degree 1, and it's like basically free on a basis given by the like on a basis related to the things you divide it by. So then the cotangent complex, i.e. the L omega 1, has Tor amplitude in 1, 1. I mean, in that case, it's even like finitely generated projective concentrated in degree 1. But so this is like similar to the situation that Ben was discussing yesterday with the quasi-regular semi-perfectoid stuff. So what do we get then for this? Well, let's think about I equals 1 first. L omega 1 lives in degree 1. Then we're shifting it down by 1, so now it's like in degree 0. And then we're twisting it by something, but it's still in degree 0. What happens for L omega I in general? Well, similarly to how omega I arises from omega 1 by applying exterior powers, you can describe this derived omega 1 in terms of this cotangent complex by applying derived exterior powers. And one can check, so that's not completely obvious because, for example, for symmetric powers it's not true, but one can check that this ends up concentrated completely in degree I. So it follows from this by some computation involving figuring out how derived exterior powers work that L omega I has Tor amplitude in I comma I. So it's completely concentrated in degree I. And maybe this doesn't show up on the recording if I write at the bottom, so let me swap these. So what do we get if we shift this down? Well, this again ends up just contributing to degree 0. And by the way, in fact, it might be easier, instead of describing L omega I individually, to think about L omega star. And it turns out you can compute that in this situation, when you're a quotient by regular sequence, L omega star looks like a divided power, like a free divided power algebra. Maybe that's a good exercise if you know something about this non-abelian derived stuff, but I haven't done this computation yet. The takeaway is that this derived Hodge-Tate comparison tells us that in this situation, or more generally, if we have like cotangent complex concentrated in degree 1, then we should expect prismatic cohomology to be discrete, right? We should expect this to just be some explicit thing in degree 0. That's good news, right? Because it's somehow hard to write down objects from homotopy theory, but there should be some explicit description of whatever the hell this prism R relative A is in that case. Yeah. Yes. Yes, I think they're both minus I, right? Over there, the twist was like a +1. And I think what we got out of Hodge-Tate comparison was a description of the thing with positive twists, but then we turned it around to describe the untwisted guy in terms of omega I with a negative twist. I think it's correct. Right. So our goal is now to focus on this special case and try to figure out an explicit description for what this prism R relative A looks like. And explicit, well, we could hope for something that we can actually play around with, some kind of generators and relations description. So let's maybe switch gears and introduce another piece of structure before we do that. So what we've not yet discussed is the Frobenius on prismatic cohomology. So the Frobenius lifts on the B that I have in this prismatic site, these give a map, like an endomorphism on global sections. So a map phi from prismatic cohomology to itself, which is semilinear, right? This is not an A-module homomorphism, but it's semilinear with respect to the Frobenius lift on my base prism, A. Right, because this was true pointwise, right? All of these Frobeniuses commute with each other. So we can also view this as an A-linear map from the base change along the Frobenius to the non-base changed guy. So this map we'll call the relative Frobenius, and it's defined on this Frobenius twist of prismatic cohomology. And this will appear so much that this deserves a notation. It's with a like 1 in parentheses on top. So this is the Frobenius twist, like the twist of this A module along the Frobenius on A. This is the untwisted version. You have this relative Frobenius. And now we haven't yet spelled out how the comparison between TP and TC minus and so on and prismatic cohomology works. Yeah. I mean, to give a tensor product, I have to provide an action of A on this and on this. And this action is the one that we already have, and this action is the one by phi. So yes, I guess this guy is viewed as an A module via phi. Right. And so this is the thing that in full generality, there's also like a relative version of this comparison result, has to do with TC minus. The case why we didn't see the Frobenius twist in what Ben wrote up yesterday is that this is like the absolute situation, and the absolute situation is in some sense relative to ZP, where the Frobenius is the identity. So, but this is the thing that generally shows up when comparing to TP and TC minus. And so remember that we had some filtration on TP0, TP2, like TP2I in general. That filtration we now want to describe. And so in the case where prism R relative A is discrete, for example, in this situation where it's like a regular quotient of A mod I, I guess I mean static, yes, but nothing here is condensed, so let me also call this discrete. But yes, I mean it just has pi 0. In that case, we define a filtration on the Frobenius twist by pulling back the Hodge-Tate filtration, meaning the I-adic filtration on the target along this relative Frobenius. So, in other words, what does it mean for an element of the Frobenius twist to lie in Nygaard filtration? This is the Nygaard filtration, so we finally know what the N stands for. So what does it mean to be Nygaard filtration bigger or equal I? It means that you're an element with relative Frobenius being in this ideal I to the I or I guess maybe I should write this as this. Right, so in the case where we're really dealing with a principal ideal, and that's basically what we'll be dealing with most of the time, otherwise it's just locally principal, but the same idea still applies. This is basically measuring how divisible does an element become when I apply this, like how divisible by my my generator D does my element become when I apply this relative Frobenius. Yeah. Yes, so remember in this prismatic site, so the question was, what's this Frobenius again? In the prismatic site, the objects were these prisms B, and remember they were not just arbitrary A algebras, they came with a delta structure, and we're finally starting to utilize that structure because part of what a delta structure gives you is it gives you Frobenius lifts on each of these B's, and under the limit they assemble into some Frobenius lift, or some map phi, which we call the Frobenius, on prism R relative A. And that's the phi up there, and then this is just semi-linear. Viewing it as an A-linear map, we get this relative Frobenius. But yes, so this comes out of the delta structure we have on all these prisms. So there's a board over there. So, for example, what's an example for an element that lies in positive Nygaard filtration? Well, remember this is the relative Frobenius. So, for example, 1 tensor D in this Frobenius twist. Right? Under the relative Frobenius, since this is like A linear with respect to the new A module structure on this Frobenius twist, this gets mapped to just D. And so 1 tensor D lies in Nygaard filtration bigger or equal 1. And in general, we only want to view this Frobenius twist as A module via the new A module structure. Right? I somehow could also view this as an A module structure through the old action of A, but I only want to view this as an A module through the new, like Frobenius twisted A module structure, and hence simply write D for 1 tensor D. Sorry, and when I write D, I mean, if we're in the case where we have a principal ideal generated by some distinguished element D, so one of these D with like delta D a unit, then this gives me a prime example of like an element in positive Nygaard filtration. Okay. So here's a warning, which is, so here I did something underived, right? I pulled back a filtration along some map of just discrete things and really view this as a filtration by sub things. So warning, in general, the maps that I get from like the graded of this Nygaard filtration to the graded of the Hodge-Tate filtration on the other side. So this we just wrote as this twisted version of right, so this was just tensoring this prism bar with some power of I. These maps are injective, but not surjective. So if you think about this pulling back a filtration really as describing the n bigger equal I as like pullbacks, this is really like underived pullbacks. So this is a subtle point, and so a priori it's not clear how to get a version of this Nygaard filtration in the case where this prismatic homology is not discrete. So one can or maybe let me say this here. So it's not surjective, but it has image given by this conjugate filtration guy that we saw earlier. Right, we discussed this as a filtration on prism bar, but I can of course tensor by that line bundle. Yeah. Well, sorry, yeah, I have the order wrong. So in this case, in this discrete case, it's not injective, but it has that image. And then it's not surjective, but it has that image. And then there is a Nygaard filtration, just in full generality on this derived prismatic cohomology. Oops. My tablet is talking to me. Tried to give me the Oxford Dictionary definition of derived. Don't know what I touched. I didn't listen, but maybe I should have. So there is such a Nygaard filtration on the on derived prismatic homology in general, and it's obtained from this one. So by not left Kahn extending, right? Because here we're more in like a regular quotient of A mod I type situation, but one can extend this to a Nygaard filtration on the Frobenius twist of prismatic cohomology for general R by quasi-symptomic descent. So this uses a version of what Ben discussed yesterday, that you can somehow still cover every R by, or at least every quasi-symptomic R by something whose cotangent complex over A mod I really lives in degree 1. And in that case, prismatic cohomology is discrete. You can take this definition and you can descend that. So it's a bit indirect to describe this explicitly, but this generally a filtration, so this gives a filtration on the Frobenius twist, so where the relative Frobenius now generally gives equivalences between the ith graded of this Nygaard filtration and this ith piece of the conjugate filtration on Hodge-Tate cohomology with this twist. Yeah. Yes. So there was a question: how do you get this now in full generality on like any R? So I've been slightly imprecise here. So if we take this thing seriously that I said earlier, that on general R you really want to look at this derived prismatic cohomology, then to get from this discrete situation to general R, you first have to write Kahn extent, so do quasi-symptomic descent to get something on all quasi-symptomic R, so in particular polynomial rings. And then you can left Kahn extent from that. And on quasi-symptomic things, this doesn't change anything, so this really gives like something that agrees with what I said here for quasi-symptomic over A mod I. And for general ones, it's like the non-abelian derived thing of that. So yeah, it's a bit subtle. It's kind of like a complicated sequence of steps that end up all being compatible, but not a priori, right? So, yeah. Well, I guess it's like maybe without the semi-perfectoid, just quasi-regular, if that makes sense. So just the condition that the cotangent complex is really concentrated in degree 1. Although I guess you can get both, right? You can maybe also get a map from a perfectoid by... You can always like do something like adjoin all roots of P and then quotient by... Yeah, I don't know. You can do this, but yeah, I think it's sufficient to cover by something with like cotangent complex in degree 1. All right. So now finally, let's think about this regular quotient case, and let me now look at a situation where my ring R is like A mod I, comma, some R. And let me, for simplicity, assume that we're in this oriented prism situation where this I is really a principal ideal generated by some distinguished element D. And now let's take a regular quotient of A mod I by a single element R. So an object of the prismatic site consists of a prism B comma J and a diagram like this. And now think about it. What does it mean to have such a diagram? This map here is just surjective, right? So it's really not a condition, like it's not extra data to have this map. It's really just a condition. And the condition is that we have a prism under A such that R gets mapped into this ideal J, right? Because that's the thing you need in order to factor through this surjection. You need that the element R becomes 0 over here, so it ends up in the kernel there. And now, so if you've been wondering, like, why exactly are we putting these delta structures on things? What's the purpose of that? I think one of the main points where you see that in action is here. Thinking about how many ways there are to build a prism under A, where this R also ends up in the in this ideal, right? It somehow needs to basically become divisible by that ideal. And here's a lemma, which is if A is a delta ring and we have elements D, U, and D prime with two conditions. The first condition is that delta of D is a unit. And the second condition is that A is complete with respect to P and D prime. Then U and delta D prime are automatically units. So basically we're starting with a distinguished element, and if that's divisible by anything that's in a sense topologically nilpotent, that guy also has to be a distinguished element, and they can only differ by a unit, right? So this kind of very sharply tells you that divisible elements, distinguished elements are kind of unique in a sense, or I guess follows that they're uniquely determined by the ideal up to units, something like that. And the proof is remarkably simple. We just apply delta. Apply delta to this, you get delta of D equals delta of U, delta of U times D to the P plus U to the P times delta of D prime, sorry, this is a D prime, plus P times delta U times delta D prime. So modulo P and D prime, this is just U to the P times delta D prime. So here we've somehow decomposed a unit into a product of two things. So these two things are also units, at least modulo P comma D prime, but we're complete with respect to that. So we have to be units upstairs as well. Right, so this is kind of remarkably simple, but it somehow is what makes all of this tick, because one corollary is that if B comma J is a prism under A comma some ideal generated by some distinguished element D, then J is automatically just the principal ideal generated in B by D. You get that by thinking about what it means that D is being mapped into J and that B is J complete, right? You're exactly in the situation up there. So this is, by the way, what I also used under the hood earlier when I said that the associated gradients of the Hodge-Tate filtration are really just all twisted with I. There I also used that on the whole prismatic site, these ideals J are all just base changed from I. And so what does it now mean to have a prism under A where R ends up in the ideal? Well, it just means that in that other delta ring B, R becomes a multiple of D. And so here's a very important lemma, which is that the prismatic site let me put maybe an op here. In the case where R is like A mod D comma R, and this is like a regular quotient as earlier, has an initial object of the form, take A, adjoin a new element, and by these curly braces here, I mean adjoin in the world of delta rings. So this can be explicitly written. It's a little lemma. There are free delta rings, and they take the explicit form that you adjoin like delta powers of your generators. And then you impose one relation, namely that D times A is R. And you also have to kind of not just quotient by that ideal, but by the closure of that ideal under delta. And you can also explicitly write this as dA minus R, and apply delta to the whole thing, and so on. And then this whole thing needs to be a P comma D complete A module. So you have to complete it. A is any prism where the ideal is principal with a single, like with distinguished generator D, and R is a non-zero divisor on A mod D. So I really want this to be a regular quotient. Then this has an initial object. There's like an initial prism where R ends up in the ideal J, and it's of this form. And another notation that is kind of suggestive for this is you take A, and then in the world of delta rings, you adjoin an element R divided by D, right? That's all we did. We adjoined a new element, but we made it be like R divided by D. And then we complete it. No. Right, you might have started with something like, so example, you could start with something like one of these polynomial or power series things with distinguished elements, say Z plus P. Then A mod D is just a copy of ZP. And so we could take R equals Z mod P to the N, right? That's a regular quotient of this A mod D. So that's an example where this applies. And so we get in this situation where we're regular quotient. So I've only told you how this works for one relation, but in fact, if you have a sequence, like a regular sequence of relations, you get the same kind of formula where you've made like R1 to Rn divisible by D. So we always have in this discrete situation that I was setting up earlier an initial prism in this prismatic site, and it's always of this form. So somehow, even though our ring R is like smaller than A mod D, right? We've imposed more relations, we've killed things. Prismatic cohomology, right? If this has an initial object, this already is prismatic cohomology. Maybe put this here. Prismatic cohomology just gets bigger. We just adjoin these fractions to it. So all we've done by imposing this relation on R is that we've made the element R divisible by D up here. And when I write R here, of course, yeah, I guess if you think of R as an element of A mod D, you have to pick some lift in A. Yeah. Right. So this is called a prismatic envelope. This is like the one case in which prismatic cohomology is just a completely explicit algebraic construction, nothing derived. And next talk we want to explicitly study this and try to figure out what this actually looks like as a ring. Sorry for going a bit over time. So the question was what goes into Hodge-Tate comparison, and it's a bit tricky, but basically since the proof in Bad Scholze goes over like multiple chapters, but essentially they reduce it to an explicit computation, I think, in the case of a polynomial algebra. Ah, okay. So apparently in Bat-Lurie there's a more conceptual explanation. I think, but I haven't worked out whether it might be circular, because they also, of course, use Hodge-Tate comparison to establish some statements, like in what generality prismatic cohomology is left Kahn-extended and has descent and whatever. But in principle, so this might be a bit circular, but if you knew a priori that prismatic cohomology has like quasi-symptomic descent and so on, you could also try to deduce it from this, right? Because we've seen that you can get from this like case of cotangent complex in degree 1 back to the more general like quasi-symptomic case by quasi-symptomic descent. And in this case, there is like these explicit formulas, and here we've not used anything. Here we've just used that there is like an initial object in these prisms, and we'll see in the next talk how the filtrations, like how the Nygaard filtration, this conjugate filtration, and so look like, and in the end, you basically get something that really looks like the divided power algebra that you are expecting from like the derived de Rham forms. And I think this could also be turned into a proof that starts here, and then you do quasi-symptomic descent to get the smooth situation. Well, I guess so the question was whether it's automatic that D is a non-zero divisor. You mean in this lemma? That it is not a zero divisor. Yeah, maybe. Maybe I missed that assumption there. I guess we're only applying it in these cases where both D and D prime come to us as distinguished elements in one way or another. So there we have this non-zero divisor condition built into requiring that the ideal is an invertible module. No, but I mean, you could ask whether. So I guess here in the argument down here. Yes, right. I guess, yeah, a priori you don't know that the image of D in here is a non-zero divisor, but this lemma, where we haven't used anything about non-zero divisors, shows that it is actually, it differs from one of these Zariski local generators of J by a unit, and therefore it's also a non-zero divisor because this J is assumed to be an invertible module. Yeah. Right. So the question was, why do we get filtration when we derive this Hodge-Tate comparison theorem? Very good. So I think I tried to say that in words, but maybe didn't say it. So if you have some spectrum X and you have some kind of factorial description of, yeah, maybe let's think X is some factor on something, and then we have some factorial description. Yeah, maybe, yeah, let's say we have some factor X from rings to spectra. We have some factorial description of homotopy groups for polynomial R. Then one way to factorially interpret this is that the filtration given by tau bigger equals star on XR has associated graded given by Fi R in degree I for polynomial R. Right, so we have a natural filtration on X, this one, and we have a natural isomorphism between its ith graded and some functor on this subcategory of polynomial ones. And it's this description that you can derive, right? You can say, okay, think of the filtration just as some tower of spectra. So each of those is like a functor from rings to spectra. I can just left can extend from smooth guys, and I get some tower of spectra for general rings. For polynomial ones, this agrees with the original Postnikov filtration on XR, but for general ones, this might just be some filtration. But what is its associated graded? Well, its ith associated graded is also going to be the left can extension of these functors, right? It's a general trick. That's also what Ben used yesterday once we stated this HKR theorem that tells you really something about homotopy groups of Hochschild homology, of the spectrum HH R relative K. Then you could left derive that and get a statement about the left derived Postnikov filtration in terms of the derived functors of the homotopy groups. Yes? Right, there was a question about multiplicativeness. So prismatic homology is an E-infinity ring because it's like a limit of rings and of commutative rings. And all of the filtrations, basically everything I wrote down is multiplicative. So the Frobenius twist is of course also an E-infinity ring. The Nygaard filtration is multiplicative. The Hodge-Tate filtration is multiplicative. The like the prism bar, Hodge-Tate cohomology is also an E-infinity ring, and this conjugate filtration on prism bar is multiplicative, and the relative Frobenius is an E-infinity map, and like everything is multiplicative.